First of all, let me thank the organizer. It's a real pleasure to be here, and as I said, I'll be talking about quantum information complexity today. So the setting is the following. We have two parties, Alice and Bob, who each have their own private input. So Alice has input X, Bob has input Y. They're separated, but linked through some quantum communication channel. Okay. And what they wish to compute is some classical function f of their joint input, x and y. So they want to output f of x and y. And in order to do so, well, they can use quantum resources. So for now, we'll assume that they have access to a full-fledged quantum computer on the other side and quantum memories. Similarly, on Bob's side, they have access to pre-share entanglement. And then once the protocol starts, Alice uses her classical input x as well as her share of the entanglement to generate the first message, C1, that she sends to Bob. She keeps some quantum memory A1. Then upon reception of C1, Bob uses his input Y along with his share of the pre-share entanglement together with the new message just received from Alice in order to generate a new message to send back to Alice, C2, and he keeps some quantum memory BI. And so on. So upon reception of C2, Alice uses her local information to generate a new message to send back to Bob, and so forth. So they interactively communicate like this until Alice receives the last message from Bob, and then she uses this message, her input, her quantum memory, applies some quantum measurement, and what she gets is the function output evaluated at their input x and y, hopefully with high probability. Okay. So they wish to do this with the minimum amount of communication. So we essentially give them local computation for free, but we assess the amount of communication. So we're interested in the length of each of these messages. So we denote the length of the ith message, Ci, by the number of quantum bits of noiseless communication that they must use to transmit it from one party to the other. So that's what we denote by the length of Ci here. And then for the global protocol, the cost of the protocol pi is denoted QCC, the quantum communication cost of pi, and it's just equal to the sum of all the length of all the messages. Okay. Then, in order to compute a given function f, we say that the cost of the function is just defined in this way, QCC of f, the quantum communication cost of f, or communication complexity of f, and it's just defined by taking the best protocol in terms of like the minimum amount of communication, and as long as the protocol does compute function f with low error at the output. Okay. So this model of interactive quantum communication is defined by Yao in '93, and in '96, Cleveland Berman showed that, in fact, you can obtain, very excitingly, provable quantitative quantum advantages in this model. Okay. So there's different variant of this model. Of course, there's a classical variant where, well, Alice and Bob only have access to classical computers, classical randomness, and they exchange classical messages. And in classical model, you can also decide not to allow for any randomness, so the protocol might be deterministic, or you might allow for private randomness. So Alice might have some access to some private coin on her side, Bob some private coin on his side, or they might even share some public randomness at the outset of the protocol. And this choice affects a lot the amount of communication they must exchange in order to compute some functions. So an example of a function where randomness helps a lot is the equality function. So Alice has input x, Bob has input y, and they wish to know if x is equal to y. Okay. And if the protocol is deterministic, essentially they have to exchange their whole input in order to compute the equality function. Okay, they must exchange n bit of communication. But then, if they have access to private randomness and they allow for a tiny amount of error, then, well, they can do a lot better, exponentially better, in fact. So they can compute equality with only log n bit of communication in that case. And even better still, if they have access to pre-share randomness, well, they could use it to publicly sample some public hash function that they can use, and then they can just verify their string are equal with very high probability using a constant amount of communication. Okay. So with public randomness, they can even do with order 1 of communication for the equality function. But then for equality, all of these protocols can do with only a single message. So is interaction a powerful resource in this setting? So it is indeed very powerful, and with interaction, you can also get exponential advantages. So for example, for the greater than function, so for the greater than function, Alice and Bob each have a number of n digit in n, and they wish to know which one of these is greater than the other. Okay? And if they're only allowed to exchange a single message, then once again, essentially, the best they can do is, well, exchange their whole input. Okay? But then if they allow for interaction, only log n round of interaction, then they can make with only log n amount of communication here. So they get exponential saving by using this ability to interact. Okay. Even more exciting today is that, well, if you allow yourself quantum communication rather than only a classical setting, once again, you can get exponential saving for some function. Okay, so for the so-called vector in subspace problem, Clark-Dragon Reject showed that classically, you need polynomial amount of communication in order to solve this problem, whereas it's known that you can do so with only log n amount of communication in quantum setting. Okay. But here again, like the quantum solution only requires a single message. So we'll discuss a bit later one quantum problem for which the quantum advantage requires that Alice and Bob interact. Okay. And one very important choice that we need to do in this talk today is that, well, we must decide whether we wish to account for communication as we have done until now, or if instead we wish to account for a different resource, that of information. So instead of accounting for the amount of communication in the protocol, well, we might instead be interested in how much information each party must learn about the other party's input. So how much information at the end of the protocol must Bob learn about Alice's input X, and how much information Alice must learn about Bob's input Y in order for them to be able to compute the function f. So let me try to explain this link between information and communication with this simple game. Hopefully you know Who's Who. So in that game, Alice is given one particular character out of a set of here 24 possible characters, similarly for Bob. So Alice's input is Anita here, and Bob's input is Armin. So Alice wishes to determine what Bob's input is, and vice versa, Bob wants to determine what Alice's input is. Okay. So one question that Alice could start with is, well, Bob, is your input max? And she could go on like this for each of the characters. But then these questions are not very informative. So for each of these questions, like she expends at least one bit of communication, but then what she's learning is only a tiny amount of bit of information. So she would have to ask like 24 of these questions. But in fact, since there's only 24 possibilities here, she can make do with much less. So there's only essentially 5 bits of information to learn in this setting for Alice. Okay. All right, so let me give you the outline for the talk today. So start with a theory part. Well, I'll define this information complexity notion. So I'll start with a definition in classical setting in order to motivate the quantum setting. Then I'll discuss like difficulties in defining such a notion, the property we wanted to satisfy, like how it concerns privacy. And then after, discuss some more practical protocol that can handle experimental error in such a setting. Okay, so on to the theory part. So let me first recall very briefly some notion of information theory that we'll need in this talk. So in the basic information theory setting, we have once again two parties, Alice and Bob. Alice has some classical message M that she wishes to transmit to Bob. They're far apart, but they're once again linked through some communication channel, possibly noisy. So today we'll mainly be interested in noiseless communication channel. Throughout the end of the talk, we'll also consider practical protocol where we can handle lossy channel and noise detectors. Okay. But then even if they have access to a noiseless communication channel, so if Alice's message has low information content, before transmitting it to Bob, well, she would like to compress it down to its information content. Okay. But then what do we mean by information content for such a message, like in the setting of source compression? Well, so that's the first question we're wondering. So how to quantify classical information? Okay, so an often appropriate way to do this is with Shannon's information. Okay, so in a setting more corresponding to what we'll see later on, let's say that we start with some correlated input to Alice and Bob, input X on Alice's side, input Y on Bob's side, and then Alice generates some message that she wishes to transmit to Bob. Okay, some message M that only depends on it. Okay, so you can think of this as some stochastic map. Some stochastic map M given X. Then we wish to know how much new information about X will Bob learn upon reception of this message here. But given that he already knew Y at the beginning, and Y can be correlated with X. And then this conditional mutual information quantity here is often the right quantity to characterize this. Okay. So that will be our main basic information tool in this talk. So that's all well and good for asynchronous messages. Now, what about interactive messages as the one we're interested in today? Okay. So how do we quantify the amount of information conveyed by an interactive protocol? Okay. There could be multiple ways to do this. So one way would be to, well, just run the protocol and then look at what's the final amount of information which has been leaked about each other's input at the end of the protocol. Another approach would be, well, just sum the information content of each of these messages. Or a further way to do this would be to do as in the source compression case and take as a good operational measure of information the optimal asymptotic compression rate if we wish to repeat same protocol on different instances multiple times. Okay. And it turns out that, well, in a classical setting, all these three notions agree with each other. And it won't be the case in quantum setting, though. Okay. So, well, a long sequence of work has led to what's the current modern definition of information content for a protocol, which is widely accepted. And it looks like this. So essentially, it quantifies at the end of the protocol how much information has Alice learned about Bob's input through this sequence of messages, C1 up to CM, which have been exchanged back and forth between Alice and Bob. Plus, it also quantifies how much information Bob has learned about Alice's input at the end of the protocol. Okay? So in terms of this conditional mutual information, and quantify how much information the sequence of message, C1 up to CM, reveal about Bob's input Y to Alice, given that she already knew X at the beginning, and also our share of the randomness. And similarly, how much information the sequence of message reveal about Alice's input, given that Bob already knew Y at the beginning. Okay. And then in order to compute their goal, like compute function f, well, we quantify the information cost for a function by just optimizing, taking the protocol which computes f, but at the same time reveal the least amount of information. No matter how much communication the protocol has, we're interested in this information leakage for the protocol. Okay. So this is quantified in this way. So we optimize, take the protocol which has the least amount of information, and then we evaluate this over the worst case input distribution. Okay. And somehow it quantifies the least amount of privacy loss that Alice and Bob must give to each other about their input to compute this function. Okay, so it satisfies many interesting properties. So in particular, it's direct lower bound on communication. it's also exactly equal to amortized communication, as we mentioned earlier. Then it's not always clear if you can always compress down to the information content of the protocol. So in other words, like, can we always compute at the privacy limit in terms of information? Now on to the quantum setting. So in the quantum setting, an often appropriate way to measure information is instead with von Neumann's quantum information. Okay. So we have a similar measure of correlation, a conditional quantum mutual information, which is defined in formal analogy with the classical quantities. So how much information does a message C contains about some other register R, given that the receiver already knows some partial information B. Okay. So how can we then go and define information for quantum protocol, interactive quantum protocol? Okay, so, well, by direct analogy to the classical case, for a first trial might be to just try to, well, measure how much information all of these messages contain about Ali's input X, given that Bob's start with his input Y. And similarly, how much information Alice learns about Bob's input. Okay. And well, if we have quantum messages, this is not a possible way to do it, and it's not even well defined. So if these messages are quantum, the no-cloning theorem forbids us to make copies of them, and then at the end of the protocol, these messages don't live at the same time. Okay. But then another perspective on the classical information cost was to just, well, try to accumulate as much information throughout the protocol until the end, and then measure the total amount of correlation at the end of the protocol. Okay, so it's another possibility in the quantum case, but turns out that the possibility of reversible computing in the quantum setting, this is not always a nice measure of information. Instead, well, even if there's not much information left at the end of the protocol, if Alice and Bob are able to compute the function, it must be that at some point they exchange information about their input. Okay. So one other way is to try to measure the total correlation at each time step. Okay? And this has been used very successfully for a particular problem by Christian and Sen and Jen Naya in the past. But it turns out that in this way, you can still overcount a lot. So in the highly interactive regime, this quantity can be off by a factor of number of rounds. Okay. And one of the property we want for our information measure is that it's a direct lower bound on communication. So the definition I proposed a couple of years back is this one, which once again measure the amount of information each of these messages contain about the other party's input. But we're taking now a fully quantum view about the input. Okay, so we can purify the input and measure this information. And it's only accounting for the new information each message contains about the other party's input. So taking this fully quantum view, you can think of as having a similar insight to those security proof in the quantum key distribution, where like you have prepare and measure protocol, but then for security purposes, like you go to the entanglement-based view of the same protocol. Okay. Turns out that this definition satisfies all the property that we listed for classical information costs for quantum protocol. So it's a direct lower bound communication. It's also exactly equal to amortized communication complexity in the quantum setting. And well, ever since, it's been a very rapidly developing framework. I've been lucky to collaborate with many great researchers, and there's many different groups that's also been working on this around the world, for example, in Paris, Singapore, and in the US. So I think it's a very interesting framework. It's very active. So now we're done with theory part, so let me go on to the more practical part, where we'll discuss a bit about practical protocol that can also handle experimental error. Okay. So far we've been discussing a model where we allow Alice and Bob like full-fledged quantum computer on their side and noiseless communication channel, so on. Okay. But what if we wish to obtain quantum advantages not only in 10 to 15 years, but in the next couple of years, say? Okay, so can we have a more restricted model of interactive quantum communication that's still interesting and can lead to quantum advantages? So, for example, we might allow ourselves to have classical pre, mid, and post-processing classical communication as long as it has limited information leakage. This is classical processing is thing we can do very efficiently. But then we'd like to keep the quantum subroutine part of the protocol fairly simple in comparison. Okay, so one caveat though that comes from a recent work of Chayou, and Laurier is that when we mix together classical part and quantum part like this, we have to be careful how we handle private randomness. Okay, I won't go further into this, but still, well, even by taking necessary precaution, can we still obtain quantum advantage in this setting? Okay. So, in order to get there, let me first recall you talk from a QCrypt a couple years ago by Arazola and Zhu, presented a protocol developed by Arazola and Lukianhaus, and its experimental implementation reported by Zhu Arazola and their collaborator for a quantum fingerprinting protocol, okay, using coherent states. So this is in a different model of communication. So in this model, Alice and Bob are not allowed direct interaction, neither pre-share correlation or resources, and they simultaneously pass a message to some referee who must then decide for the quantum fingerprinting problem whether their classical input x and y are equal or not. And they found that using QKD technology, they were able to experimentally find some quantum advantage for this problem. Okay. So this leads us to a question we've been studying recently with Ben Levitz and Norbert Lukianhaus. So what can we do in the direct interactive setting now? So the problem I'll be discussing now is that of appointment scheduling. So in the appointment scheduling problem, Alice and Bob have as input some calendar of availability on end dates. Okay, so we can view their input x and y as a subset on a calendar of end dates. And they wish to schedule an appointment. So what they want to find is some index I in the intersection of these two sets. So a date where they're both available, or they want to determine if the intersection is empty, so if there's no date of common availability. Okay. So we can rewrite this in terms of a bit like this. So in terms of the indicator function of their sets. So in such a rewriting, yes, what they're looking for is some index I such that both Alice bit xi and Bob's bit yi are equal to 1. Okay. And it's now that for this problem, essentially the best that a classical protocol can do is to reveal almost all of the information about their input. Okay, so classically, the information leakage of this for solving this problem is on the order of the input length. But then, quantumly, we can get a square root n advantage by essentially using a distributed version of quantum search. Okay. But it's also known that, well, for this specific problem, single one-way message doesn't do. So if we wish to get quantum advantage by a factor of r, essentially, we need r round of interaction. Okay? And then we get the full quadratic speed up by using square root n round of interaction. So the question we're asking is, well, can we get something similar, but by using relatively simple quantum subroutine? Okay, so, and the answer we found is that essentially yes. So this is work in preparation. I said with Ben Levitz and Norbert Lukianhaus, and essentially the quantum subroutine part, which I'll briefly discuss, use coherent state on only over 2 modes, beam splitter, and then a lot of classical processing. Okay, so the quantum subroutine part is inspired by previous work by Jane, Christian, and Sen. And then classical preprocessing part is inspired by previous work with Bremen, Garg, Gonko, and Mao. And it looks like this. Okay, so Alice and Bob only have to look at one coordinate at a time. Okay, so for the quantum subroutine, Alice has only a single bit of input, A. Bob has a single bit of input, B. And then the protocol goes like this. So Bob starts by preparing these two current states. So a first one with constant amplitude alpha, and the second one with 0 amplitude. And then, depending on her classical input bit, Alice decides what operation she wishes to apply. Okay. And it's the same operation all throughout the protocol. And then, upon applying her operation, she sends back these current state to Bob. Okay, so now you have two current states with amplitude gamma 1, delta 1. Bob looked at his classical input and decide what operation he wished to do. Okay, so it's the same operation throughout once again, for what different from Alice. And then, upon applying this operation, he sends back the current state to Alice, now in amplitude gamma 2, delta 2, and so on. So they send back and forth these two modes, these current state over two modes. And then at the end of the protocol, after our such round of interaction, Bob applies one last time his operation, and finally sends the gamma mode into some single photon threshold detector. And similarly, sends the delta mode over some other single photon threshold detector. And he wants this to be such that, well, the D1 detector essentially only clicks in the situation where A is equal to B is equal to 1. Okay, so if this coordinate corresponds to a date of common availability. So let us just quickly look into what happens inside this A and B box. So the operations are fairly simple once again. So upon a 0 input, Alice, just applied the identity. So essentially, she just transmits back the current state to Bob. Okay. So she just sent back. But if she has a 1, what she wishes to do is essentially, she wants to slowly rotate from the first mode to the second one. Okay, so she applies some beam splitter with a beam splitting ratio essentially 1 over R, and then send the two current state to Bob. Now, what should Bob do on his side? Okay, so well, in the case where his input is 0, he doesn't want Alice to rotate all the way from the first current state to the second one. So what he does is, he just takes Alice's message, put that in the trash bin, and just re-inject a fresh alpha 0 state. Okay. But then, in the case where his input is also 1, he wants to let Alice rotate from the alpha 0 to the 0 alpha state. So he just directly sends this back to Alice. Okay. And then, putting all of this together, the only time where, Alice can flip from alpha 0 all the way up to 0 alpha is when both these inputs are equal to 1. Okay. And then we have these theoretical bounds that show that indeed we can get some quantum advantage even by accounting for channel losses and for dark counts. So the ideal quantum protocol is this purple bound there. Then accounting for these experimental errors, we can still get this upper bound on the blue bound there. Whereas it's known that in the classical setting, you cannot do better than this red bound there. And even accounting for error in the protocol, classically, you can do better than this pink bound there. So we get close to a factor of 50% improvement by using this all this classical processing together with this quantum subroutine. Okay. So let me conclude there. So we discussed both theoretical framework for quantum information complexity, as well as some possibility for practical implementation of quantum advantage in this setting. And there's a lot of very interesting research direction in this area, both on the theory side, on theory for application side, and as well as for possibly experimental implementation of such quantum advantages. Thank you very much.